Hello, Chris. Hello, Robert.
Hey, Chris.
Hello, Randy Libros, physics professor at CCP. Randy's
Randy.
here.
Hey, how are you
He's
doing?
at the same university,
Oh,
college.
Hi, guys.
Hi, John. Thanks for joining us.
Hey, Lancy, Ken, glad you can make it.
Yeah.
are there any ladies that are interested in this topic, or is it only men that are interested in this topic, other than myself?
I was in a physics study group for a couple of years, and I think there were 2 women who showed up, even though we were actively soliciting. The gender bias in the previous generation seems to have been terminal.
Well, there
Well,
are PhDs in physics that are women. I know that, and actually know some of them, but yeah.
Some exciting new books out on physics by women, including a friend of mine, Chanda Prescott Weinstein, has a new book called The Disordered Cosmos. So I can plug her book.
Do you know that Gloria Brown is here? Who, you know, you were talking about not enough women. No, she's chemistry, but
I met her at a Guggenheim soiree on Park Avenue.
I'm in the middle of one of her books right now.
Oh, well, I guess she is here, but I didn't know she was here because
Okay.
she's booting up, and I'll let her in if she promises to behave herself.
Who's that?
Gloria.
Oh, Gloria. Okay,
Yeah.
wow.
All right.
Who, me?
Yeah, we need more women.
To be sure.
We know
So-
there's quite a few women in statistics now. This is over the last 15 years, and maybe probably more than a third now.
So I'm going to start a meeting. Okay.
Okay, great.
All right. Sorry, this has been a bit delayed. Let me. I'm going to do a brief introduction of the people who are here, and then we will turn it over to our guest, Paul. Okay. So all of you know, except perhaps John Maynard and Jonathan, that we are, we're about a 20-year-old club that's met almost every 2 months, and we have fun with philosophy, and I'm sure tonight will be no exception. Linda and Robert Rosenwein are 2 stalwarts who have been here for like 10, 15 years, I would say, and also social activists and all-around admirable people. Robert Fuentes is my college buddy who studied quantum physics 50 years ago.
Okay.
And but he's a quick study on getting caught up, and he's a physician also. And Chris Hill is another good buddy who loves philosophy. At every meeting he comes to, he's thrilled, right, Chris?
That's right.
And Ken Ulancy is a very talented saxophone player, among many other skills. I only know a few of them, Ken, and has a long interest in physics. Randy Libros teaches physics at CCP, the same school that Gloria is at. And John Maynard, you want to introduce yourself?
Yeah,
How do you know?
I'm a philosopher. I've interacted with Paul and am looking forward to some of the topics that we can take up, from our understanding the reality and history to maybe some of the ethical implications that we'll find ourselves confronting in the future.
All right.
Yeah, John's very active on Twitter and has some very insightful comments, so that's how we know each other.
Fantastic. And Jonathan, you're here through Len, right?
Yeah.
You want to say something about that, Jonathan?
Jonathan, you want to introduce yourself, or should I introduce you?
Physics and engineering to layman's degree.
Anyhow, just one more thing before we begin in earnest.
How about me?
Len, I'm sorry, you're behind me.
Sure.
You're not in view. Go ahead.
Yeah, I'm a statistician, a biostatistician. I work at Einstein Hospital. I've been there for a long time. I was one of the statistical editors of Annals of Internal Medicine for 25 years. And so, you know, I got experience. I was a physics minor. That was a long time ago. But I'm interested in physics, and I studied mathematics for many years. So, you know.
All right, this is just a little introductory tease. Thank you, Len. This is Halpern's box, and this is the cat that will either be in this box or not. So we'll take a vote on how many things will be in the box or not. And then we will temporarily, he is definitely in the box, but that remains to be seen. And now we're going to go to the Paul's PowerPoint and truly begin. Yeah, I'll tell you in a second. So, okay, want to go to full screen? Next slideshow.
Oops.
Okay, you can control this wheel if you like.
Okay, so how do I click forward? Just
Maybe you could try the arrow, when the arrow keys apply to it also.
oh, okay. Let me just. Great. Okay, so I want to thank Albert for inviting me, and this is actually my first philosophy club, so I'm really honored. I feel privileged to be among philosophers and people interested in philosophy. I've spoken before at astronomy clubs. I've spoken at critical thinking societies, skeptics groups, but this is my first philosophy club. So today I'm going to be speaking a little bit about the Schrodinger's cat paradox and placing it within the context of all the quantum conundrums it's associated with. It has a number of references to different types of quantum conundrums. So first of all, I can't talk about Schrodinger's cat without talking about the personality of Irwin Schrodinger. He's a very interesting person, brilliant person. He spoke many different languages. He was originally from Austria, but part of his family was English. So he spoke German, English, Spanish, Latin, brilliant thinker, very interested in Eastern philosophy. And he developed what's called the Schrodinger wave equation. So that was the thing in physics he's most famous for, is an equation that's supposed to show how electrons behave in atoms. And it imagines, in his interpretation, the electron as being something like a blob. And I hear some sound from somebody's computer. Could everybody mute themselves?
Maybe it's me.
Yeah, I think it's our speaker.
It might be me. Okay, here's Jeff Berger.
Okay. Anyway, that's better. Okay, sorry to interrupt. But anyway, so Schrodinger was very interested in Eastern thought. He wrote a lot about Eastern philosophy as well as quantum physics. So he was very much influenced by philosophy, which is appropriate for this talk. So Schrodinger's cat, which is what he's known for in modern times, has become a modern emblem of ambiguity. And in some ways, it's a bit of overused emblem. People talk about Schrodinger's this or Schrodinger's that as being anything which is contradictory. And for example, there's a cartoon, Schrodinger's parrot, making fun of the Monty Python parrot sketch, where a parrot is half alive and half dead because you don't know if it's deceased or living. And so it's a little bit of a play on the parrot sketch and on the idea of ambiguity. So I was kind of proud that this cartoon was shared by Eric Idle from Monty Python on Twitter. That was kind of my Monty Python claim to fame. Now, curiously, a little bit about Schrodinger, he was as contradictory as his cat. So first of all, he loved fresh air and exercise, but he would drown others in the smoke from his pipe. He was a chain smoker, but would go out to the mountains while smoking. He would go to a conference dressed like a backpacker and not be admitted until people vouched for him because he kind of looked like he was hiking in the mountains. But then he'd go to the beach with a suit and tie and bring a blackboard and do calculations on a beach. He told people he's an atheist, but he was always talking about divine motivations. His love life was very strange because he was married, but he had a number of kind of second wives, third wives. And at one point he lived with both of his wife and another woman who was the mother of his first child, a young woman named Ruth, a girl named Ruth, I should say, who didn't really know Schrodinger was her father until later in life. And she passed away recently, and really came to really admire him, and she kind of forgave him for not revealing that he was her father. So I don't know, since it's close to May the 4th, Star Wars Day. I don't know if he said like, Ruth, I am your father. So I don't know if it was a Star Wars kind of introduction like that.
That was bad. That was almost bad taking a blackboard to the beach. Just
okay. So anyway, and his doctoral work, he was an experimental and theoretical physicist, and he also considered switching to philosophy, but he stuck with science, fortunately for science, unfortunately for philosophy. And a colleague of him said that he was like he was always being chased from one problem to another by his genius, from one country to another by political powers in the 20th century. He was a man full of contradictions. I should say another contradiction is that he left Germany because of the Nazis and tried to find haven in another country. But because of his complex marriage, he had a lot of trouble finding a job. So then he went to Austria, and the Nazis annexed Austria the following year. So he was stuck back in Nazi Germany, even though he'd escaped from Nazi Germany. So he tried to please the rulers by writing a letter in praise of Hitler, even though he didn't believe in that. And he was fired anyway from his job and had to escape to Ireland. So he went to neutral Ireland. So it was very strange, his political career. And then he apologized for that letter and said he just had to do it to try to keep his job. So very strange character. So he was obsessed in terms of physics with the question of how the cosmos is connected. So now let's kind of delve into the heart of physics. In physics, there are many different ways that things can be connected. Cause and effect is just one way that things can be connected, kind of like dominoes falling. But there's also the possibility of correlation, things that have a common cause and are correlated, but are not directly related by cause and effect. There's also pure coincidence. Things can happen and there's really no connection. There's chance. In physics, we have the possibility of pure randomness in some quantum events. And finally, quantum entanglement, which I'll talk about in a little bit, which is a causal connection between events in which information could be shared over a great distance. So let me talk briefly about some of these connections before going into the cat paradox. So first of all, causal connection. So an example in physics would be lightning strikes. We know that lightning is an electrical discharge, and lightning strikes a tree, and the tree topples. The tree is struck by lightning, tree dies and topples over. We know that's a clear cause and effect. So that is an example of causality, and the tree falling happens after, in terms of time, the lightning striking. And if you measure the events very carefully, you know that these transpire at the speed of light or less. So lightning travels at the speed of light, but causality's upper limit is the speed of light. It normally is slower than the speed of light. So one way of gauging a causal connection is saying, is it at the speed of light or slower? If it's faster than the speed of light, then there's a suspicion that it's not a causal connection. There's statistical correlations. For example, lightning and overflowing gutters often happen at the same time, but we don't say that the lightning strikes the gutter and causes it to overflow. It has a common origin, which is a thunderstorm causes both to happen. Then there's pure coincidence. Sometimes theatrically or in a movie, there's a lightning storm right before a scary visitor appears, but that's pure coincidence. Dracula just happens to arrive right after the lightning storm. And finally, sheer chance. Well, an emblem of chance is a dice throwing, roulette wheel, tossing a coin. So these are what we think of as sheer chance. But remarkably, if you're good enough at measuring things, you can take things that are apparent chance and turn them into something that has to do with causality. So, for example, a group of physicists, they call themselves eudaimonics, and there's a book about it with a strange title, Eudaimonic Pi. They were a group of physicists who decided to challenge the roulette wheels in Vegas, Reno, and elsewhere by using mini computers in their shoes that were operated by their toes. And they managed to beat the roulette wheel for a while before the casino started to get suspicious. So that's a good use for physics.
So what were they?
Well, they observed the roulette wheel. They would observe a single wheel and measure how long it would take to land, and then put into some algorithm, and the algorithm would say, if the wheel is at a certain number, what's the most likely places it would land based upon the dynamics of that particular roulette wheel. So anyway, I interviewed Doyne Farmer, who was one of the members of the group who became very successful at predicting the stock market and other things later on in his career, in addition to being a respected physicist. So he's still active. But strangely enough, quantum mechanics became reinterpreted. I mentioned, sorry, I left out an R in Schrodinger, but I mentioned that Schrodinger was famous for his wave equation, describing electrons as kind of a blob moving through space. But then what happened was Heisenberg came up with another interpretation of quantum mechanics involving pure mathematical chance. Heisenberg calculated the odds that an electron would suddenly move from one quantum state to another quantum state. And then Max Born, who worked with Heisenberg, came up with a matrix method for doing this, and also showed that the Schrodinger equation doesn't describe waves of matter, but rather describes probability waves. It describes the likelihood of an electron being anywhere in a region rather than being at a particular point. So while Schrodinger thought of his wave as literally a cloud of charge and matter, kind of like literally if you took a blob and you observed how the blob was moving, Max Born turned that into the probability that the electron would be somewhere. And that became something that needed to be measured. So there was an extra step. You need to measure where the electron is, and the probability wave tells you the odds of where it is. Now you might think, well, if you're really good at roulette, you could use a computer to calculate these odds. But the strange thing about quantum mechanics is the randomness is fundamental. You can't beat the odds. This has been shown again and again in quantum experiments that there's a fundamental built-in randomness to quantum mechanics. Schrodinger was very upset by this. He said to other quantum theorists, if he had known that there would be these random quantum leaps, kind of like a flea jumping from one place to another, he never would have gotten into the business in the first place. He found it ridiculous. And he, for the rest of his life, he tried to find other ways of explaining quantum physics. So he became one of the quantum critics, even though he was happy to pick up the Nobel Prize for his equation, and gave talks about that. But he also gave talks about the paradoxes of quantum physics. And then he found an ally in Einstein, because both Schrodinger and Einstein read a lot of philosophy. They were interested in Schopenhauer's idea of will, of an invariant will, and Spinoza's idea of divine determinism, that the divine is constrained to make certain decisions, and that actually is how nature works, that nature is deterministic, that one thing happens after another like a chain of falling dominoes. And Einstein was probably stronger on the belief in determinism than Schrodinger was, but they both talked about continuity, they talked about local objective physical states, and chance being an artifice of artifact of having a large system that's impossible to predict. But if you could look at things on a small enough level, things should be deterministic. But quantum physics had other ideas. It does what it wants, and it shows a built-in randomness. It shows non-locality. It shows discontinuity. So there are a lot of things in quantum physics that are very strange. So I wanted to mention the idea of quantum superposition, that until you measure something, a state, sometimes it could be in a mixture of possibilities. For example, an electron in a box might be anywhere, but until its position is measured, you don't know exactly where it is. You measure its position, and it's said to collapse. The wave function collapses into one of many different possibilities. Now, one thing that's present in quantum physics that isn't present in classical physics is the idea of spin. And spin is key to understanding quantum physics and the idea of entanglement. So Wolfgang Pauli, a physicist, showed that electrons can't be in exactly the same quantum state. They can't be at the exact same energy level. There must be at least one thing different about them. So if you take two electrons, bring them together, they're not going to like to be the same. One of them is going to become different in some way. The difference turns out to be something called spin, which is how they orient with respect to a magnetic field. And they don't really spin, but they act as if they're spinning magnets. And one of them is spinning up, the other is spinning down. So that's why it's called quantum spin. They really are not spinning, but they act as if they're spinning magnets within a magnetic field. So we call these spin up and spin down. So if you put two electrons together, you know that if one is spin up, the other is spin down. Now, until you turn on a field, magnetic field, the electron is in a superposition of spin states. So if one is up, the other's down, but you don't know which is up and which is down until you take a measurement. So that is very strange, because if you put two electrons in a box, you know that one is up and the other is down. Now, if you separate the electrons, you know that one is up, the other's down, but you don't know which is which. And now entanglement is when you separate them indefinitely and you measure one of them, the other one must be the opposite. So we'll see how that works. So let's say you take electrons, you separate them, then you take a measurement of one, its wave function collapses from a superposition, which is an equal mixture of up and down, into either up or down. So one of the electrons is going to be either up or down instantly once you take a measurement. Well, what's going to happen to the other electron? Well, if one of them is up, the other must be down. So that gives you quantum entanglement. That superposition can span large distances, and somehow one of the electrons knows what the other's state is instantly, okay? They share a state. To make things even weirder, you can orient a magnet in 3D, 3 dimensions. So you could put it in the X direction, the Y direction, or the Z direction. If you take one magnet and put it in the X direction and measure one of the electrons, and it gives you spin up relative to the X direction, immediately the other electron knows that with respect to a magnet in the X direction, it has to be spin down. So it not only knows it has to be opposite, knows it has to be opposite in that direction. Well, how is that information shared? Many people thought that there's some kind of hidden variable or hidden mechanism in which that information is shared. Einstein hoped that that was something to do with an extra dimension or some artifice, some connection with general relativity. But, and Schrodinger hoped that maybe there's some unity in nature that shows how things are connected. But many, many experiments have been done showing that there are no hidden variables. There's something called John Bell's theorem in quantum mechanics, which shows that how to determine whether there's hidden variables in an experiment. And so far, it's never been satisfied. There's never been the possibility of hidden variables. And Einstein called this spooky action at a distance. And he published a paper along with two colleagues called the Epr Paradox, trying to show that there's a paradoxical situation. It didn't involve spin, but later it was reinterpreted as involving spin. And he seemed to suggest in his paper that you could find a way of measuring a connection between the electrons and know perfectly what the states are, but that turned out not to be. And the New York Times published an article famously which said Einstein attacks quantum theory. So made headlines. Now, in the lead up to Schrodinger's cat, Einstein proposed a couple of thought experiments. One of them was, could dynamite be in a mixture of exploded and unexploded states, quantum dynamite? Because it could be in a superposition. Well, could dynamite be exploded and not exploded? That sounds kind of ridiculous, right? He also said, well, what if a mouse took a quantum measurement? What if a mouse measured dynamite and the dynamite was in a box and you didn't know if it's exploded or not exploded? Would it automatically become one or the other? Very, very strange idea. Well, Schrodinger was in correspondence with Einstein, and that's when he came up with the cat experiment. So finally, the cat experiment. So let me describe the cat experiment, which Schrodinger published as a paragraph. It's a single paragraph in a paper on quantum entanglement. It's the paper where Schrodinger coined the term quantum entanglement. And the cat paradox is, imagine a cat in a box. And you close the box. So we have a box here. Imagine the cat in the box. So there's a cat in a box. We don't know if it's there or not. Okay. And imagine you cruelly put in the box a flask of poison. And you put a hammer connected to the flask. And you put a Geiger counter connected to the hammer. And then connected to the Geiger counter, you put a radioactive sample. Well, radioactivity is a quantum phenomenon. So if you had a radioactive sample of the right type, it could be the type that has a 50-50 chance of decaying in a certain amount of time, let's say an hour. So the sample has a 50-50 chance of decaying, but until you measure it with the Geiger counter, and because the Geiger counter's in the box, you wouldn't know if it's decayed or not decayed. So the sample would be in a superposition of decayed and not decayed until you opened the box and took the measurement. Well, if it decays, it sets off the hammer, which breaks the flask, which releases the poison, which kills the cat. If it doesn't decay, the flask is intact because the Geiger counter doesn't tick. The cat is fine. The cat is alive. Well, you have a soundproof box. Well, until you measure the material, you don't know if it's decayed or not decayed. It's in a superposition of states. Therefore, the cat is in a superposition of being alive and dead. So it's a zombie cat until you open the box. Very strange. But Schrodinger did not believe that that was real. He believed that there was a ridiculous implication of quantum mechanics. First of all, he thought that quantum mechanics should only apply to particles. That doesn't apply to anything beyond particles. And secondly, he didn't really believe in this idea of superposition. He believed that there must be some way of determining objectively whether the cat is alive or dead. Therefore, there must be a way of determining objectively if the sample was decayed or not decayed before you take the measurement. Well, quantum mechanics says you have to take the measurement first. So it's very strange. So there's one way, I don't want to go into much detail, but I can do it in the question session or discussion. One way out of this, and it's imagining that the universe splits into parallel realities. So in one reality, the cat is alive and we open the box and we're happy. In the other reality, the cat is already dead and we open the box and we're sad about it. But our minds bifurcate too, and our existence bifurcates. So we're now in a quantum superposition of two universes, but we don't realize we're in a superposition. So the cat stays in a superposition of alive and dead. We stay in a superposition of being happy that the cat's alive, sad that the cat's dead, and we live the rest of our lives in that superposition, not realizing that in this parallel universe, the alternate reality occurred. And the other one of us doesn't realize that. So it's very strange. Hugh Everett did that as part of his PhD thesis. And Bryce DeWitt later dubbed the idea the many worlds interpretation of quantum mechanics. And it's a controversial idea. Only a minority of the community believe in it. So as mentioned, in recent years, Schrodinger cats become a cultural meme. I'm going to conclude my 20-minute talk, hope it didn't go over, with two jokes. One is a cartoon published in the New Yorker about your cat, Mr. Schroedinger. I have good news and I have bad news. And then here's another depiction of the zombie cat in cartoon form. Okay. So anyway, I as you may or may not know, I write books about physics, popular books, and one of them about the cat is Einstein's Schrodinger's cat, and a more recent book is Synchronicity, and I have to plug yet another book about the Big Bang Theory, Flashes of Creation, which is coming out in August. So if you're interested in quantum weirdness, those two books on the screen are probably the most to do with quantum mechanics. If you're interested in the Big Bang Theory, pick up Flashes of Creation, which is available for pre-order, and be glad to talk about that someday. So anyway, can open up the floor for questions, either from live people, virtual people, people who are in a mixture of live and virtual, in a superposition of being alive and virtual. If you want me to take a measurement and find out which is which, let me know.
Let's thank our speaker first. I did not do a good job as a host of introducing you. I apologize, Paul. I was somewhat bamboozled.
You can say something about me if you want.
Well, he's, besides having written, 20 or 30 books, he has a great ability to make the difficult facile or more understandable than otherwise, which endears him to so many people. He has many wonderful videos on YouTube of all varieties, and we're lucky to have him here in Philadelphia. So thank you for coming. And that's just a bit. I mean, there's much more about your Guggenheim Fellowship and awards and distinctions that you could mention a few if you'd like.
Yeah, Gloria mentioned earlier about Jana Levin. And one of the nice things about Guggenheim is that every 10 years I get to go to a party on Park Avenue. So as I'm not a very rich person, I have to reveal that. It's my one opportunity. Once every decade, I get to go to Park Avenue in New York to an apartment and go to the Guggenheim party. And the second one the first one I went to was when I got the Guggenheim Fellowship, and the second one, I got to meet Jana Levin, another author, who got the Guggenheim Fellowship for her science writing. So it's a really cool thing. But there's also artists and photographers and so forth. So yes.
We have a question from John Maynard.
Yes, thank you for recognizing me. The Bell incompleteness theorem is an enormously complicated work. I've been trying to tackle it, especially in preparation for this, because I know that it's important. But I think I noticed that what came from it in general terms is that, it proved quantum physics or demonstrated the viability of quantum physics. I think what struck me was, well, I think I need an explanation of it because it's very complicated. Thank you for recognizing me.
Okay. So it is very complicated. I think what Bell was trying to do was to say, okay, suppose an electron, so we have two entangled electrons, and you have electron 1 and electron 2. Now, suppose electron 2 has access to information about electron 1. Then there's behind the scenes information, and that will lead to certain types of correlations, certain statistical correlations.
Yeah, I remember the EPR explanation of it, where they said it was like mittens and the orthogonal relationships.
Yeah, so you have these, yeah, so you have these orthogonal relationships in Hilbert space. I guess what you're referring to, and you have all these possibilities. So the electron, if it already knows what it's supposed to be, it has access to all these states, all these possibilities. It's either there's the state spin up, spin down in the x direction, spin up, spin down in the y direction, spin up, spin down in the z direction.
We need a natural limit for these.
Pardon?
We need a natural limit for these, like the speed of light in the
Yeah, right. So in other words, that access has to take place in the speed of light or less for that information to be shared. But then, so Bell said, okay, this is the limit. This is the limit given the speed of light, given that the electron has access to this information. This is the limit for how much correlation you can have between the states. But if you exceed this correlation, if the electron somehow exceeds that limit for the exchange of information, then there can't be hidden variables. There must be some other way the information is shared.
That was the hidden variable.
Yeah. So, and Bell was actually hoping that it would come up with a hidden variables explanation. But in consequent years, every experiment has showed that Bell's inequality is violated, meaning that things are conveyed acausally. So
yeah, it's really weird. It's one of those challenges to the integrity of science that just keeps proving right.
Yeah, and they keep trying to find loopholes to it. And if you go to talks on quantum measurement theory, they all have the term loophole in it. They'll be like, a loophole-free explanation of this. And then someone will find another loophole and they'll say, okay, to eliminate that loophole, we're going to send the equipment out into space. Or to eliminate that loophole, we're going to do the measurement after these other things have already happened. So there's all these objections to experiments, and people try to counter these objections. So it's a whole industry.
Yeah.
Thank you. Good question.
I didn't want to interrupt, but I'm very excited.
Thank you. Linda?
You're muted.
Sorry, I can't hear you. Can you turn on your mic?
Some of what you talked about is decades old in thinking. And I would like to know in the last 10 years or so, and I saw a little bit of some of this development in the Wikipedia. What are in a layman's way of explaining, are the major advances or ideas that are somewhat new in the way people in physics think about quantum mechanics?
Well, first of all, there's a lot of technological advances. People are trying to build quantum computers that rely on superposition of states. So there's a big race to build larger and larger quantum computers, but they're very expensive because you need to cool them down to close to absolute zero for them to function. And you need to protect them because once something interferes, then there's a phenomenon called decoherence, and they start to collapse into classical states. So you have to protect them. But quantum computers basically are things like these electrons that stay in a superposition of states, and then they interact with other electrons. But you don't have to use electrons, you can use light particles too. And you can set up a whole network of things that are in a bunch of states at once. And then you take a measurement and all these dominoes fall, and then you get an answer from the quantum computer. So that's one area that's very exciting. Another area is just basically these, entanglement experiments. More and more sort of teleportation and entanglement experiments.
I mean, it sounds like there's things like the envelope around the possibilities can be lumpy in shape. The people have theorized those kinds of things. It sounds like more and more in the math, they're looking at little tweaks of the theory.
Well, they're looking, the quantum theory is well established, but what they're doing is trying to interpret it, so different interpretations, because the idea that somebody taking a measurement affects the result is kind of weird, because then Einstein said, well, what if a mouse takes a measurement? What if an intelligent dolphin takes a measurement? What if, on and on, like what if a dog pushes a button? Is that an observer? So there's this whole question. And then why is the observer separate? Why is Niels Bohr thought the observers in the classical world and the experiments in the quantum world? Well, why make that separation? So Hugh Everett came along and said, well, the observer and the observed are in the same world. It's just a complicated world that has many parallel universes, but people don't like that idea. So there are many different interpretations. Then there's the issue of testing these using teleportation experiments, entanglement experiments, and finally the practical application. So there are 3 different levels of quantum physics. Any other questions?
I have a question. Can you
Yes,
explain
Nate,
basically
Norman?
fundamentally,
Okay.
Nate,
Jonathan speaking.
no, this
Can
is
you,
Jonathan.
explain fundamentally what
Oh,
Can't-
Jonathan.
what the nature
Jonathan, we can't hear you too well.
compatibility between-
Jonathan, could you get closer to your microphone,
Can you
please?
hear me now? Is this better? Can you hear me now?
A little bit.
Yeah, I just moved. Can you hear me now?
Yes.
Better.
Can you hear this?
Yes.
Okay. Can you explain? Okay. Can you explain fundamentally what is the incompatibility between quantum mechanics and relativity, and what is the nature or the problem that makes them incompatible?
So could you repeat it? So the question is, what
you
is
hear
the
the question?
incompatibility between quantum mechanics and relativity?
Mhm.
Well, there are 2 kinds of relativity. One is special relativity,
That's
which
correct.
is Einstein's 1905 theory of how things work at close to the speed of light. And that actually has been reconciled with quantum physics. There's something called the Dirac equation, which predicts how an electron behaves relativistically and under quantum mechanics. So that's not a problem. The problem is general relativity, which is Einstein's theory of gravity. The problem is gravitation is a continuous deterministic theory. So if the sun disappeared suddenly, it would create a wave, a gravitational wave in space, and that wave would travel in between, hit the Earth and knock the Earth out of orbit. Or another example is two black holes collide, create ripples in space-time, travel through space, and are picked up by a detector. And that, we know that to happen. We've had detectors pick up gravitational waves. But the question is how to quantize this, how to describe this as particles of gravity, or what's called gravitons. Well, people have tried to develop theories, mathematical theories of gravity using quantum mechanics, and every single theory ends up with answers which are infinite. So you try to do a calculation, you get the answer infinity. And no one's been able to get rid of the infinities. And there are attempts to try to reconcile the two, but none have been successful so far.
I have a
Is there
question. Linda, did you get your question in?
Undefined-
Linda, did you get your question
She
in?
did, yeah.
I was out of the room.
Yeah, I did. I did have another question, which is another one of those theories that I understand there is no way to get experimental data to prove is string theory. And I'm wondering what the relationship is between string theory and quantum theory.
String theory is the idea that fundamentally, on the deepest scale, there's no such thing as a particle, that an electron is not a dot, is not an infinitesimal dot. In quantum theory, we say, well, the electron itself is an infinitesimal dot, and then we describe its probability using a wave. In string theory, you go one step further and say, well, the electron itself is some kind of wave in a string, and that there's no such thing as something that's a point. There's no points. The smallest thing is a line segment. Once you do that, you get rid of things that have zero size. Everything has a finite size, kind of like, you know, a shoelace, or instead of a dot, something like that. Well, the advantage of that is that if you do mathematical calculations with something that's finite, if you take 1 divided by the size, which comes up a lot in quantum theory, say take 1 divided by the size, you don't have 1 divided by 0 anymore, you have 1 divided by a finite number. So all the terms become finite, meaning you don't have infinity anymore. So that's the advantage. So that's why people like string theory. But the problem is, you can predict almost anything using string theory by using the vibrating strings. You can predict not just the known particles, but you can predict hundreds of thousands, millions, billions of other particles, states. So you have to narrow things down from trillions and trillions of possibilities to a small set of possibilities. And no one's been able to do that.
They had some good people working on it. I hear about Ed Witten a lot.
Oh, yeah. He's a very humble person. I really admire Ed Witten. Very, very humble. He's worked on string theory for years, but unlike other people, he's never tried to capitalize or commercialize his fame in the field.
Yeah.
He's always stayed very quiet. He's never written a popular book. And I met him, at Ed Witten.
Tell him the peanut gallery's asking about him.
What?
Tell him the peanut gallery's asking about him. We want a popular book.
If I see him again. I met
stuff is really great.
I met Ed Witten once. There was a ceremony to honor the Institute for Advanced Study where Einstein worked. And that ceremony was in November 2016. And it was the day after the 2016 presidential election. And people were a little bit weirded out one way or the other. by it, and some people were just kind of in a state of shock. And that's where I met Freeman Dyson, a famous physicist, who was like, "Oh yeah, I could have predicted that." Freeman Dyson was kind of like, "Oh yeah, you know, he thought he knew the American public, even though he's British." And Ed Witten was kind of very quiet. So I took a selfie with Dyson because Dyson was fine about that. But then I met Witten and walked around with him and talked to him and introduced myself. But he was so quiet, I didn't even really ask anyone to take a photo of the two of us. Now I have some regrets, but you know, the problem is on social media, they say pics or it never happened. So like if I said I met Ed Witten, I don't have a photo to prove it, so people won't believe me.
Well, I want to ask a question. You may have covered it already, but are there good examples of quantum entanglement at a great distance that have been proven demonstrable experiments? Because I've talked about entanglement to some of my friends who are very well educated, and they say the idea that one particle at the other end of the universe can correspond to another is bogus science, and Einstein didn't believe in it, so it's probably baloney.
Well, they've done experiments in space with entanglement, but there are commercial examples which make use of entanglement. There's a property of matter called superconductivity, where you have all these electrons that, first of all, pair up. So electrons pair up, and then all these pairs link up like what I say, marching soldiers, marching in unison, and they're always aligned, and it's like soldiers marching through a field, and then they cross a bridge, and they don't lose step. They're always in lockstep. And these electrons behave that way, so you can have perfect conductors, which you put in some impurities, the electrons don't see it, they just keep moving. And that's called a superconductor. It's a conductor which never loses energy. So if you had a superconducting wire from Niagara Falls to Philadelphia, you could convey power from a power plant in Niagara Falls to Philadelphia without losing energy. The big problem with superconductors is most of them require extreme cold, but they're also used in Japan in magnetic levitation trains. So superconductors are an example of entanglement because you have these coherent states over great distances that march in perfect lockstep. So one end immediately knows what the other end is doing. So that's an example of entanglement.
Did astronauts ever have like an experiment where there's this electron has this spin and it matches something? And
well, they do that. They do that with photons, with light particles. They shoot them up to satellites. There was a Chinese satellite called the Mycia satellite, and these researchers in Vienna shot a beam of